Okay. All right, so, yeah, the sapling chapter 8s are due, they're due in the last week of class, I believe. They're not due before the next test, but the more you do, and those are outlined in the folders for the day. It'll tell you what problems are appropriate. So the more, I think, if you do those, they're going to be like the problems in class for the next exam, which is Friday when we come back. All right, so we're talking about electrophilic additions to alkenes. And there's a few more reactions that we want to talk about. Oh, great, it's already written in for me. So, maybe we'll add some stuff to it. All right, so as far as the reactions we've talked about so far, we've talked about hydration, H plus H2O, mercuration, demercuration, and then the HBr with the peroxide. HBr with peroxide, HBr without peroxide, H plus H2O, and mercuration, demercuration. So let's add a couple of reactions to this. I don't think I can erase any of this stuff. It'd be helpful if I could, but I doubt that I can. No. Okay, so next reaction is going to be electrophilic addition to form bromohydrins. Okay, so for bromohydrins, what we have is we're going to add bromine and water. That's what we're going to add to the double bond. And so our electrophile is going to be Br plus, and our nucleophile is going to be water. So far, our nucleophile has been either water, bromide, chloride, and our electrophile has been usually H plus, although it was mercury in the case of H, or in the case of the mercuration. So what I'm going to do is I'm going to add a Br plus and then a water to this. So I'm going to add a Br and OH. So three things we still need to know. Every reaction, what am I adding? I'm adding a Br and an OH. How? Markovnikov. But there's no H plus. So how do I know that it's Markovnikov? We got to broaden our definition of Markovnikov. We broaden it so that the electrophile is H plus. So in other words, when Markovnikov when he came up with this rule, which he didn't come up with, he didn't do work even close to this, but somehow it got labeled to him. He basically, we talked about H plus being the electrophile. So our modified Markovnikov should say the electrophile goes to the carbon with the most hydrogens, and the nucleophile goes to the most substituted one. We know the reason for that. The reason for that being that we add the electrophile to form the most stable carbocation. That's what we know. So in this case, the bromine, the Br plus, is going to add to the carbon with the most hydrogens. I just add a couple hydrogens there. The nucleophile is going to add, the water is going to add to the carbon with the most number of alkyl groups. So it's Markovnikov from that standpoint. So we're adding BROH, Markovnikov, and then the third question is 100% cis or 100% trans. Well, when we add the bromine, when we add Br plus to a double bond, we get this bromonium ion, which you have the uncluttered version of. Bromonium ion gives a triangular intermediate. As soon as you have the triangular intermediate, you know you get 100%. The triangular intermediate always gives 100% trans. So that was the case with Br2. That was the case with mercuration, demercuration. So whenever you get a triangular intermediate, you will always get trans addition, 100%. Okay. So if we're looking at this reaction and then that the reaction can be regioselective because it's Markovnikov, and then it could be stereoselective because they add 100% trans. The operative words there being could. You got to take each problem on its own. So let's say that I was to take that alkene, basically take this alkene, which I think is actually reversed of the previous page, but that's fine. I'll take that and I'll add Br plus to it. Now, instead of the Br plus bridging, let's write the Br plus and make it have a choice. So it either adds to the left-hand carbon A or the right-hand carbon B. So if I do that, that's where I get my regioselectivity from. I take my pair of electrons, I add my Br plus. If I add it to the molecule on the left, let's see if it'll let me finish off the CH3. Yay, it will. This morning it kept erasing it on me. So the Br, if I add it to the carbon with the CH3s, the other carbon becomes a carbocation. Why is there a line through this? Because it's a primary carbocation, which I'm only allowed to draw, to then put an X through it. So that's not going to be a very stable intermediate. If I add the Br plus to the other carbon, carbon B, then what do I get? Then I get the plus charge on the tertiary carbon. So that's a tertiary carbocation. And that's a more stable one. So this is how we always explain Markovnikov's rule. We just say you're going to add the electrophile to the carbon that gives you the most stable carbocation. In order to do that, the electrophile has to add to the carbon with the least alkyl groups and therefore the most hydrogens. And it has to, the carbocation then is left to form on the most substituted. That's when the nucleophile is going to add. So here is my major intermediate. So that's how we explain the regioselectivity by Markovnikov's rule. And then you could do the same thing with the mercury. If you didn't quite get how mercury was Markovnikov, same thing. If this was a mercury ion, I could do the same analysis and the mercury would add here, and then that's where the plus charge would go. The mercury later gets replaced with hydrogen. So that gives me Markovnikov. But what this doesn't tell me is what actually happens in the mechanism. This explains the regioselectivity, but it doesn't explain how we can translate this to the triangle. Okay? So everybody kind of with me? This is why we get bromine added to the CH2 and OH eventually added to the tertiary carbon. But now what I have to do is now I've got to translate that to the triangle. Because if this was really the mechanism, how would the water add to that carbon? Well, it would add 50% cis and 50% trans, and we know that does not happen. We know that it has to be 100% trans, so this carbocation cannot be a pure carbocation, or else we would get 50-50. So what do we have instead? We've got this bridge. So how do we explain regioselectivity in terms of the bridge? Stereochemistry is really easy. Got a triangle, nucleophile has to add underneath, trans. So here's what we need to think about. It's kind of anticlimactic with all the stuff already written on there. Water. What kind of nucleophile is water? It's weak. So it will have to react with either a full-blown carbocation or the carbon here that's delta positively charged. How did those carbons get delta positively charged? Because really when the bromine sits on both of them, it transfers the positive charge to both carbons. There's not very much bromine charge there. There's not much positive charge. Bromine's an electronegative element. It doesn't want it, so it just passes it on to the carbon. So you could X that out if you wanted to. Water is a nucleophile. In the electrophile nucleophile world, the nucleophile being electron rich, and this one isn't that electron rich because it's neutral. It has to donate to the poorest electrophile. So this is a nucleophile, has to add to the poorest electrophile. That's the world they live in. Okay? You can debate that whether or not that world exists outside of this, but that's for another class. The electron rich always give to the poorest of the electron poor, and the rich never give to each other. So, the water has to add to the carbon here that has the greatest delta positive charge. Which carbon is that? It's kind of anticlimactic because greatest positive, delta positive, is pointing towards A. So carbon A has the most delta positive charge. Why? Because it's more substituted. So in other words, this looks like, and I have in quotes here, a tertiary carbocation. This looks like a primary carbocation. They're not, it's not a full-blown tertiary carbocation, so it's got to have quotes. So the more substituted carbon will take on the greater delta positive charge. And so the water has to add to the carbon that has the greatest delta positive charge. That means that it's the least electron rich, or it's the most electron poor. So the water will add to that carbon. And so when it adds to that carbon, because of the bridged bromine, it has to add underneath. And when it adds underneath, then that pair of electrons goes to the bromine, it swings up, and we've added our water and our bromine. So when we talk about the triangle, this is how we explain the regioselectivity. We have to explain it based on the delta positive charge. The carbon with the most delta positive charge where the weak nucleophile will add. And the carbon with the most delta positive charge will always be the one that's more substituted. Mary?
So the bromine is getting electrons out of them?
Yeah, because these are partial bonds, so what will happen is this bond will break, and then the bromine over here will form its single bond. So it just swings over. We'll talk more about the triangular intermediate, I think, when we get back. And when we do, I'll talk about this being basically backside attack. So it has a characteristic of SN2 from the stereochemistry point of view. Now, when I've done this in the past without you watching the video, I've said, which one do you think it'll add to? And people will argue, well, it's going to add to the one that's most substituted, or it's going to add to the one that's least substituted. Usually the argument for the least substituted one is sterics, but because this is a weak nucleophile, this has to have a significant SN1 characteristic. And remember, SN1, the big issue with SN1 is tertiary goes faster than secondary, faster than primary, because we have stability of carbocations. So from the water's perspective, it has to add there. And we'll talk about if it's not water or neutral later on, because it may switch.
So is the only SN2 characteristic the backside attack?
The only SN2 characteristic is backside attack.
Okay.
And we know that happens because we always get 100% trans addition. If we didn't, then we'd have a full-blown carbocation that it would add to.
So this is the transition state on that stretch right there?
No, the transition state, that's the intermediate. Let's see if I got a blank slide. The transition state would look something like this. You'd have your bromine, you'd have a partial bond to the carbon, you'd have a partial bond to the water, you'd still have your carbon there, you'd have another partial bond there, Your oxygen is going from neutral to going to become positive. This carbon was slightly positive. This carbon was slightly positive. And the bromine is on its way to be neutral. So that would be more realistic of what the transition state is. So I know there's a lot of partial bonds in there because the partial bond started with the triangle itself.
So what you had on the other side with the triangle, without the water group attached,
That was the intermediate.
So will we draw a transition state from the first step to that intermediate?
Yes. And we'll draw a mechanism of that in a minute or two.
Okay.
Or well, you'll draw it. I already drew it this morning.
And it won't form that carbocation one that you had as well.
You won't. See, that's the thing is you will not see. You actually, for this mechanism, you don't draw these two. But why did I draw them? I drew them to reinforce the idea that this is why we get Markovnikov addition. And if we drew it out this way, if we made the bromine make a choice, then we would immediately say, oh, well, the nucleophile is going to act in a more stable carbocation. Then I took a step back and said, now how do we explain that with the triangle? And the way we explain that with what really happens is that carbon has greater double positive charge. Carbon A. So that would be our transition state. Then the final, so then as far as, let me write a clean, so that's what the arrows would look like. So the carbon-bromine bond is breaking so that in the end I'm going to have the oxonium ion, the carbon-bromine bond, like that. So that's going to be after the water adds to the intermediate, I'm going to get that as my structure. And then the final step would be to lose the H plus to then give me the OH there and the bromine there. So that would be the complete mechanism for adding the water, forming the oxonium ion, then losing the H plus. Everybody kind of with me? Or have you already started your vacation? Apparently a good number of people have already started their vacation.
You should bring some bonus points.
I should. Maybe we'll need to have a quiz when we get back.
Oh, that's a new way of applying them.
I'll probably do that anyway.
Okay, so what was our point? Our point is this is forming a bromohydrin. Br and OH, Markovnikov, trans. Now, if I wanted to write the mechanism, here would be the mechanism for the reaction of cyclohexene with Br2 and H2O. So let's imagine that, let's just start with this. Methyl cyclohexene plus Br2 and H2O. If I give you that problem, I'm going to say write the major product, could say write the mechanism, and ultimately I'm going to ask you, is it regio, stereo, both, or neither? Okay. So if I'm going to write the mechanism for this, the mechanism is going to involve taking the double bond, having its pair of electrons move towards the bromine, and then having the pair of electrons go with the bromine. So I'm going to end up adding a Br plus and losing a Br minus. That's going to be my mechanism. then I'm going to end up with this bromonium. This is my bromonium ion intermediate, where I've got the bromine partially bonded to the two carbons. The methyl group is, if this is, let's say, above the ring, the methyl group is below the ring. But both of these carbons will have a delta plus charge. Okay, so there's my bromonium ion intermediate. Then the water will come in and add to which carbon? The one with the most positive charge, the one that's most substituted, which is the top carbon is tertiary, bottom carbon is secondary. So the water will add to the tertiary carbon. And when it does, I guess I missed an arrow here, that pair of electrons will go to the bromine. So I've got an arrow of the water coming in and hitting this, attacking this carbon, then the carbon-bromine bond breaking and going to the bromine. So now I end up with the oxonium ion and the bromine. And the critical part of that, of this oxonium ion, is that the water that's been added, the oxonium ion, is trans to the bromine. So it doesn't matter whether you put them on a boulder dash wedge, that's irrelevant. What is very relevant is that one's on a dash and one's on a bold, because they got to be trans, because that's what happened with the triangular intermediate.
So we're getting a racemic mixture, correct?
Right, you get a racemic mixture of this because the bromine could be sitting on the top and the water adds underneath, or the bromine could be sitting on the bottom and the water adds from the top, and that would give you both enantiomers.
Okay. And then it's stereoselective because you can't get this.
It's stereoselective because of the fact that these two groups always add trans.
Okay. Cis,
No, they're adding trans.
yes, this is a possible product, but stereoselective because it chooses trans.
Right, we'll come back to that in a minute. All right, so there's our oxonium ion intermediate, then we lose the H+, and we get our final product. And the reason I show that mechanism is, at this point, I start getting lazy and I start going, add water, 2 steps, minus H+, to the final product. And I'm allowed to do that, but you're not. So you've got to show you've got to show the oxonium ion. Okay, and you want to make sure you always add neutral nucleophiles, the whole thing. Don't start breaking them up. So here's my final product with the OH and the Br trans. So now, after that, we would say, is this reaction regioselective? Yes or no?
Yeah.
Yes.
Yes.
We in agreement with that?
Yeah.
You guys are in agreement, actually, instead of switching back and forth like you normally do.
So we'll say no.
Synergy.
Well, you want to say no because that's wrong. Yes, it is regioselective. Why is it regioselective? Because having the OH on the top carbon and the bromine on the bottom and switching those two produces structural isomers. Did it select one over the other? Yes, because it's Markovnikov. So there is a different product form if I add the OH top, bromine bottom, and vice versa. Gives me 2 products. Did I choose one? Yes, the Markovnikov. So therefore, this reaction is regioselective. I take that methyl group away.
It's not.
It's not. Because it's a symmetrical alkene. All right, is it stereoselective?
Yes.
Yeah.
Yes. Now let's drill down a little bit more on stereoselectivity from yesterday. Yesterday I introduced the idea of stereoselectivity and said, well, you need a chiral carbon. Actually, you need at least 2 chiral carbons to be stereoselective. And the reason for that is, if I just have 1 chiral carbon, do I do reactions where I get an unequal mixture of enantiomers? No. So it takes 2 carbons to make diastereomers. So in this case, did I make 2 chiral carbons? Yes. These are both chiral carbons. Did I make 1 diastereomer over another? Well, the way we make diastereomers here is 100% cis, 100% trans. We'll give you 2 different diastereomers. Did I select one of those 2? Yes. I got trans. Cis is a possible product, but it's not formed. And the cis product would give me both of these on bold wedges. That would be diastereomers. So I selected 1 diastereomer over another. 100, 0, that's selective. And so this reaction is an example of both. And the problem sheet and the problems that I had yesterday, if you look at them, all you'll see is just the same reaction, only what I did was I started with cyclohexene. Then I made it methyl cyclohexene. Then I made it dimethyl cyclohexene. Then I usually made it methyl ethyl cyclohexene. Same product essentially you're going to get, but every time I put a different group here, I can change whether it's stereo or regioselective. And there is, I think there's answer keys. I'll post an answer key for that. I didn't post, I don't think, I might have posted those problems yesterday. If not, I'll post them with the answer key if you want to try those. Okay. So, there's bromohydrin. Now, if I wanted to do this reaction and replace the water with an alcohol, then instead of an OH up here, I would get an OR. HOH, ROH react the same way. And so instead of an OH group, I'd get an OR group. Okay. So when you talk about mercuration, demercuration, it's mercury, water, followed by the sodium borohydride. That adds H and OH, trans Markovnikov. But one of the things I can do is I can change that OH to an alcohol, and if I change it to an alcohol, then I've got alkoxymercuration, demercuration. So then I add H and the OR. We could also do that with H plus H2O. H plus an alcohol. It's not H and OH anymore, it's H and OR. So they're all exactly the same. Great. So, what can we add to double bonds? HCl, HBr, H plus H2O, mercuration, the mercuration, demercuration, HBr, and peroxide, which adds anti-Markovnikov. And then now I can add Br2 and Br2 in water and Br2 in alcohol. All right. So that's quite a few reactions. But same 3 things. What am I adding? Markovnikov, anti-Markovnikov, 100% cis, 100% trans, 50-50. You got to know that for every single reagent. Now let's talk about how to do anti-Markovnikov addition of H and OH. Because so far all I can do is Markovnikov addition of H and OH. I can do anti-Markovnikov addition of HBr with the peroxide. So if I want to add HBr Markovnikov, HBr. Anti plus peroxide. How do I add H and OH anti-Markovnikov? That was a quiz question from yesterday, one of yesterday's online quiz, was how do you do that? The answer was none of the above, because we don't know reagents to do that, but now we will. We're going to use borane and H2O2. So borane is either BH3 or it can be B2H6. You'll see either one. I'd say you see either one in your book, but let's be serious. If your book's still shrink wrapped, you might want to, you'll get prime dollar for it. But if you look online, sapling uses B2H6 for BH3. All it is two BH3s put together. That's really what the reagent looks like. So I'm going to use borane and hydrogen peroxide. So I'm going to add H and OH. The reaction yields the anti-Markovnikov product. So it could be regioselective. The H and the OH add to the same side of the double bond. Now that's new. No triangle for this one because triangle means trans. It adds cis, so it could be stereoselective. So it's a new reaction. Right, so here's what I'm going to add. I'm going to add my BH3 to my double bond. And I'm going to make this alkyl borane. And then I'm going to replace the boron with H2O2, which then replaces the BH2 with an OH in exactly the same spot. It's like what sodium borohydride, NaBH4, does with the mercury. Puts a hydrogen for the mercury in exactly the same spot. Peroxide, OH, exactly the same spot as the boron. So let's deal with the cis addition first. Okay, so here's the mechanism for the cis addition. So I've got a carbon-carbon double bond here, and then I've got my H and my boron. Now boron is one of the elements that is less electronegative than hydrogen. So that means hydrogen has a negative charge and boron has a delta positive charge. And that we're not used to. We're used to hydrogens being delta plus. So that's what happens with borane. That's BH3. If you add another hydrogen to it, it becomes BH4 minus, sodium borohydride. H minus is hydride. That's the name of it. So if I look at this and I orient it this way, along with the carbon-carbon double bond, the arrows flow from the hydrogen-boron bond to forming a CH bond. The CC double bond moves to form the carbon-boron bond. And the arrows have to move that way. You can't reverse them. The reason you can't reverse them is because the electrons have to move towards the positive charge. The arrows always move towards the positive or delta positive species. Okay, so you got to get the arrows going in the right directions. That makes this transition state, basically. So the hydrogen partially attached to the carbon, the carbon partial double bond, carbon partially attached to the boron. So now I get a square. Well,
Why is hydrogen partially negative?
over here, because its electronegativity is greater than boron's. So boron is less electronegative than hydrogen. So is aluminum. Those are the two big ones that create H minus. Well, any metal with hydrogen, the metal hydrides, but boron is not a metal, it's a metalloid. But it has less electronegativity than hydrogen. It's unique. So that makes the square. What's important about the square transition state? Well, it makes it go cis because there is no way that you have enough distance here to add the hydrogen to one side of the double bond and add the boron to the other. A four-membered ring is not big enough to bridge between the top and the bottom of the double bond. A five-membered ring is not big enough to bridge.
Six.
Maybe 6, 7, When you get into that type of a transition state, then you would add one on top, potentially one on the bottom. But for 4 and 5 member transition states, you have to add the two things cis. Now, the triangle involved two things. The triangle was the intermediate, and then something added to the triangle. When we do 4 and 5 membered rings here, both things are adding at the same time. There is that difference. And so the H and the boron added 100% cis. The boron then, when I add the H2O2 to it, that boron is going to be replaced with an OH in exactly the same position as the boron was placed. So if the boron added cis, after the peroxide, the H and the OH are cis.
What's the mechanism? Should we just draw the picture?
The mechanism of that is beyond the scope of this class. That means that this is a mechanism that I will not ask you on a test to draw.
Can Sapling ask us about it?
I don't know that Sapling does ask you. If Sapling asks you about it, it only asks you about this step. But I don't remember that it does. It may, but no one goes into this step. And we're not going to either. Okay. So that means this one I would not ask you on a test. You may say, well, if you're not going to ask us on a test, then why show us at all? I gotcha. But the reason I show it to you is the reason why. So if you get stuck on a test and you go, I can't remember if it adds cis or trans, if you think square, okay, then it has to add cis. Kind of.
So the remaining product is BH2 and OH?
That's the first product. The first product is BH2. Then when you add peroxide to it, it changes the BH2 to an OH.
Okay.
So it's a two-step process, just like mercuration, demercuration was.
And what's the ions that are left from that then after?
Oh,
You got BH2.
there's a boron. The boron has a whole bunch of OH groups attached to it.
Okay, so it is.
It becomes like boric acid.
Okay.
That mechanism primarily falls in the, like what we would call inorganic chemistry. But that's not for this class.
It's the inverse of this class.
All right, so cis. H and OH add cis. How about anti-Markovnikov? Where's that come from? Well, I have two choices when I add the H and the B in the boron. I could add the H to carbon 1, boron to carbon 2, and I'd get this one. If I reverse that, I'd get that one. Well, it turns out that the boron likes to add to the carbon that's least sterically hindered. So in this case, I would always add the boron to the least sterically hindered carbon. There is a reason for that, but I won't get into that right at the moment. And I really won't. I always say that, but then I always get into it. I'm not going to now. Okay, so that means the boron adds to least sterically hindered carbon. The H added to the one that has the most substituents, anti-Markovnikov, because this will become an OH. And you can kind of see that a little bit here with the groups. So hydroboration oxidation, anti-Markovnikov addition of H and OH, cis. Okay. So now what we have is we have 3 ways to add H and OH to a double bond. The more ways we have to do this, the more productive organic chemistry will be. One of the reasons why we can do a lot with organic molecules and make different molecules very specifically is because we always have this yin and yang. For instance, free radical halogenation, what do we have? The ability to add to the most favored position by not statistics but by selectivity, but then we could raise the temperature and have it go to the statistically favored. So we had the ability to do both of those depending on what product we want to make. Well, same things here. If I want to add H and OH Markovnikov, use acid, water, use mercury. I can even go a step further and say, if I don't care if the H and the OH add 100% trans or 50-50, then I could use this. If I really want it to be 100% trans, I got to use that. I don't have a cis way right now. We will eventually, probably. There is a cis way, but we'll get there. If I want to add an anti-Markovnikov, use hydroboration oxidation, and I'll add the H and the OH anti. Now what I'm missing there is I'm missing a trans anti. And I do have a way to do that. We do have a way to do that, which we'll get to.
We have so much to get to.
Well, yeah, we got a whole second semester. Plus like 2 more chapters. No, we just gone to chapter 9. We're in 8 now. So when we come back, we're going to talk about other reactions to double bond, not electrophilic substitutions. That's the last of those for the moment. We're going to talk about these triangular intermediates called epoxides. Guess how they're going to react? Probably trans, because it's a triangular intermediate. And this will give us a few more reactions that we can do. So that's what we'll talk about. So no video to watch over break. No online quiz. When we come back on Monday, I'll pick it up from here. And then there will be one. Well, let's see. Wednesday will be our review day for the test. And I'll post this and some other things and the answers to those problems online.